Audio Jungle. Audio Jungle.
Force vertex here. This is what force vertex. So I told you that vertex motion has suppose started. So if the continuous torque is what applying, then it is called force vertex. We already have discussed last class. So if the continuous torque is what applied, so it will be the force vertex. So means external torque will not be zero. It will be continuous. It will be continuous. And at the same time, if you go for the free vertex, so free vertex means that external torque will be zero. So how the vertex is, why and how the vertex will be there, because torque becomes zero, then how the vertex motion is there? So it is because of the condition, because of the inertia, you can say, because initially you had given torque, but if you remove the torque, then still circulation will be there, still vortex motion will be there, and later on it will be die out, right? So that is the free vertex. So but force vertex means forcibly we are trying to rotate the flow around any point. So means the point is, in case of the force vertex, torque will not be zero, it will be the continuous supplying. Okay, torque will be continuously supplying to the fluid. So because of that, whatever the motion you will get, it will be the force vertex motion. It will be the force vertex or force vertex motion. All right. Now what will be the equation, governing equation for this force vertex? Because now you know torque will be a constant, torque will be not zero, torque will be there. So definitely the fluid will be continuously rotating. As I told you last class also, I told you, suppose this is the bucket of water. Here you have filled the uh, bucket of water, and you just uh, here you are rotating your hand. Here you are rotating your hand, something like this. So fluid will be rotating. So once you are continuously rotating your hand, so fluid will be continuously rotating. So that time angular velocity will be constant, because you are continuously rotating the fluid. So it means the angular velocity is what constant, right? Once angular velocity constant, that is the one property came from the force vertex. So always remember, force vertex, in case of the force vertex, angular velocity will be constant, number one. Number two, torque will not be zero. But at the same time, if you say free vertex, so you entered your hand inside the fluid and you are rotating your hand. So water is what rotating. But if you remove your hand from the bucket, then still water is rotating. So once you are removing your hand and still water is rotating, that is called free vertex. So force vertex means you are continuously supplying the torque. Free vertex means torque becomes zero. Okay. So always remember, once you are continuously supplying torque, torque is not zero, then obviously angular velocity will be constant, means it will be continuously rotating. It will be continuously rotating. Fluid particles will be continuously rotating about a point. Okay. So that is called a force vertex. So in case of the force vertex, angular velocity or rotational speed is what constant. What is the angular velocity? Basically, if you know the formula, V is equal to R omega. This is the formula. Okay. If omega becomes constant, then V directly proportional to R. So means whatever the tangential velocity you have, like here I have shown you. Okay, here suppose in the previous case, just I had shown, suppose this is the vortex motion, this is the vortex motion. So if it is force vertex, if it is force vertex, so whatever the tangential velocity you have here, this is the tangential velocity, suppose v theta. So whatever the tangential velocity it will have around this point, this is nothing but radial distance. So it is nothing but v theta is directly proportional to r. That will be the force vertex. Radial distance increasing means tangential velocity is what increasing. But at the same time, in case of the free vertex, if you see, v theta and r means tangential velocity and radial distance both are inversely proportional. In case of the free vertex, if you are increasing the radial distance, tangential velocity is what decreasing. But at the same time, in case of the force vortex, because we know v is equal to r omega, this is the basic formula, you know, linear velocity is equal to radial distance into angular velocity, right? So v is equal to r omega, this formula you know, and also we can derive also, but no need to derive this small formula. It's a basic formula and you are aware with that. So v is equal to r omega. Omega become constant in case of the force vortex. Hence v into r, which is nothing but tangential velocity into r, is what directly proportional. So now overall, if you go for the free vortex, so last class I had shown the plot also. V theta into perpendicular distance is constant. So if you draw the graph for the free vortex, you will get it like this. But in case of the force vortex, what will be the graph? See, in case of the force vortex, if I say this is my radial distance and this is my tangential velocity v theta, so v theta is directly proportional, means that graph will be something like this. This is what v theta directly proportional to r. If you combine force vortex and free vortex, then what will be the graph? So graph will be something like this. We are talking both. Radial distance r and tangential velocity. It's nothing but this is the combined, okay? This is the combined graph C O A and B. Always remember, here it is v theta directly proportional to radial distance, and here v theta inversely proportional to radial distance. This is for free vortex and this is for force vortex. Okay, this is what force vortex. You always remember this, all right? Now, if you go for the combined flow, the combined flow is nothing but a tornado, the best example of the force and free vortex. So I will write a note also here if you want. So the note is combined force and free vortex. If it is combined, then that type of vortex called as Rankine vortex. What it is called? Rankine vortex. Rankine vortex, which is, this is the important note, so please write down, which is combination of forced and free vortex, which is combination of forced and free vortex. Okay, now what is the best example of Rankine vortex? So always remember Rankine vortex, which is the combination of forced and free vortex. Okay, what is the best example of this combined flow? Is nothing but tornado. So always remember, tornado is not only force vortex, tornado is not only free vortex, it's a combination. And if simply you can see, suppose the tornado has been started. Okay, so it's like once where it is started, and why it is starting, it is because of the pressure balancing, or pressure is what suppose unbalanced. So from one place flow will go to another place. Okay, so in that way, that from multiple direction the flow is what coming, so then this vortex formation will be there. So initially it will be the force vortex, but later on it becomes free vortex. Okay, it becomes free vortex. So it's a combination basically, and it is around this point, it is around this axis. So this is the combination of forced and free vortex that you need to remember. What is the outcome of this free vertex and force vertex we have discussed? So you always remember two types of vertex I have explained you. In short, I can give the important point here. That is nothing but free vertex and force vertex. Okay, that two important point. पकड़ो इसको. Important point here. In case of the free vertex, you got your tangential velocity is inversely proportional to radial velocity, and here you got tangential velocity directly proportional to radial velocity. This is very important. Second point is very important, and they are asking in exam. Always remember free vertex flow. Always remember free vertex flow is irrotational flow. Irrotational flow. And in case of the force vertex, it is called irrotational. Irrotational. You know, if it is
सर दोनों इधर
sorry, this is wait, rotational. This is rotational. Sorry, rotational. Okay, rotational flow. Or you can say not irrotational. Not irrotational means it is rotational. So always remember, if it is irrotational flow, if it is irrotational flow, omega angular velocity will be 0. Xi, which is vorticity, that will be 0. Okay, and obviously it is also given curl V cross V vector cross product. This value will be 0, called irrotational flow. And for the rotational, you all are aware angular velocity does not equal to 0. Vorticity, it does not equal to 0. Curl V vector does not equal to 0. This point you need to remember. This is very special, very important. And free vertex, once it becomes free vertex, then it will be irrotational flow. Okay, you know very well, if force is continuously imparting on the particles, so that particles will start rotating about the point, so it becomes rotational flow. But if there is no force or there is no torque for the particle, so that particle will not rotate about its own axis. That is the one simple reason I am telling you. But actually the rotation about its own axis or not rotation about its own axis, it is because of the shear force, and that shear force comes from the that viscosity. Okay, so also the viscosity is the main reason for the rotation. I will also discuss sometimes when it comes. But meanwhile, here you have to remember, if it is free vertex, it will be considered as irrotational flow. If it is irrotational flow, then it becomes ideal flow, approaching towards ideal flow or potential flow. So that time you are free to apply Bernoulli equation. So here, in case of the free vertex, Bernoulli principle or Bernoulli equation works here. Okay, always remember this. Also they can ask, because question from here they are asking. Okay, kinematics, this is the kinematics part. So question they are asking from here. So always remember, in case of the free vertex, if it is the free vertex flow, so Bernoulli equation or energy equation will work here. Bernoulli equation you can apply in free vertex here. Here Bernoulli equation you can apply, but in case of force vertex, Bernoulli equation you cannot apply. So for rotational flow, obviously losses will be there. Once losses is there, then Bernoulli equation is not applicable. But in irrotational flow, because there is no rotation, so there is no friction loss, so you are free to apply energy equation, means Bernoulli equation you can apply in case of irrotational flow. Okay, always remember, this is also very important point. You have to remember that. All right, now coming to the next, which is very important, called circulation. called circulation. So we have to discuss about the circulation. So basically, if you back to back, because we are talking about the angular velocity, we are talking about the vorticity, so and we are talking about the vortex flow. So back to back, we have to finish circulation also here, because it is also related to that only. So basically, circulation, you can understand this circulation comes from the circular word. Okay, I mean circulation. If we are saying, then it means it is related to the some curved flow or some circular flow. Okay, all right. So always remember in that way. Now, what is the circulation? So circulation is what, suppose if you take any curb path, okay, take any curb path here. So circulation is the line integral. Just try to understand, it's very simple. Listen carefully. Circulation is line integral of tangential velocity around a closed contour, around a closed contour in the flow field, in the flow field. Okay, it is denoted by gamma. This is denoted by gamma. Okay, what is the mean of it? It's very simple. Closed contour means what? In a flow field, the closed contour can be anything. Okay, that closed contour can be a circle, it can be a rectangle, can be a square, anything, but it should be closed. Okay, so I'm the best one. I can take this diagram. This is the now closed contour. This is the closed contour in a flow field. Suppose the flow is what going on. The flow field. This is now flow field. Huh? Flow field is what going on, something like this. Now, if so, how to define the circulation? So circulation is nothing but it's a line integral of tangential velocity around a closed contour. I can consider this is the closed contour here. See this part. This is the closed contour complete. I have taken the section. I can take the tangential velocity. I can take this element here. This elemental area is nothing but you can say ds, and you just draw the tangent to this closed contour. So tangent will be something like this, and tangent to the closed contour will have, obviously if you draw the tangent, then you will get tangential velocity, because the flow is what continuous, fluid is what flowing. So tangential velocity you will get, and you can assume from this surface to this tangential velocity, the angle is what, theta. So how to mathematically, what is the mean of the circulation? So mathematically you can write mathematically circulation, because it is noted by gamma. So it is the line integral. It is the line integral of closed contour. Hence you can give the closed symbol. This is the symbol of closed contour. Okay, line integral of tangential velocity, which is nothing but v theta. Okay, line integral of tangential velocities. If you are taking line integral, so what is the line integral? See, this is the line integral. You are taking line integrals, you have to multiply by the elemental length of the that contour. Okay, so here like dr is the elemental length, so I can write dr also you can write. I'm taking the ds is the elemental area basically. Okay, elemental area, or also you can say elemental length also in terms of dx and dy. It's your choice. So v ds, and this is nothing but obviously a vector quantity, because if I say even though area or elemental length also, it's a vector quantity. So this is now the mathematical representation of the circulation. So circulation is what, when they are talking about the tangential velocity, it means if there will be the circular flow, there will be the circular flow. That's the reason they are talking about the tangential velocity. So this circulation also related to the vortex. Circulation is also related to the vortex motion. Circulation is also related to the rotational motion. For that reason, I'm saying here, for that reason, we have to learn this circulation. So basically, the concept of circulation can be understood through the uh, very special type of flow that you just now you had seen. It's a vortex flow. So in vortex flow or in circular flow or in rotational flow, this circulation will be used to define the circular flow, to define the rotational flow, to define the vortex flow. We are using circulation. Okay, so basically uh, that circulation also related to vorticity. I will prove and I will show you how that circulation is what related to vorticity, and how that this circulation is what going to use to check the rotationality of the flow. That also we have to do. Here only you need to understand the definition of the circulation. Here mathematical model of circulation you need to understand. So circulation is generally, it is the line integral of tangential velocity around a closed contour. Now around a closed contour, if they are saying, so for that reason I made here the closed circle I have made. That's the reason, because they have said it is closed contour. Now you can understand if it is a complete circle. So for the complete circle also, if it is complete circle, so for complete circle also, if you want to write, this is now circle, this is also closed contour. If somebody asks you to write the circulation for this, so what you will write? You will write circulation is equal to line integral of tangential velocity v theta into ds, into ds. Ds is the elemental length, right? Elemental length. Now if you take any points, you can take, this is a and exactly near to this b, so you have to integrate from a to b. If you integrate from a to b, now this is what the circle. So what will be the integration? It is 0 to 2 pi v theta. What is the elemental length? To check the elemental length, you have to break it and you have to check. It is now a and it is now b. If radius is what, suppose r for this circle, radius is r, then what is the length? Elemental length. Your ds you have to integrate from a to b. So what will be the length? It is nothing but circumference, and it is nothing but 2 pi r. Simple. The total length a to b. So ds is nothing but, basically, if you see, it is nothing but 2 pi r, right? It's nothing but 2 pi r if you integrate this. Okay, so generally this is the ds only. If you check this circulation, so circulation is nothing but v theta into 2 pi r. Now this is the mean of it. Okay, so what is the v theta? Tangential velocity for the circle, it is nothing but circulation upon 2 pi r, which is very, very important. Okay, which is very, very important. Understood or not? Because this ds, if you break in terms of radial and r and theta terms, so this ds will be r d theta. If you integrate here, so it's nothing but 0 to 2 pi v theta r into d theta. So instead of d theta, you have to keep 2 pi. So it is v theta r into 2 pi. So you will get v theta into 2 pi r. So for the circular, if there is the exactly circular motion, so you will have tangential velocity, and that time tangential velocity will be circulation upon 2 pi r, where r is nothing but radius. Circulation is nothing but, suppose here the circulation we have gamma, this is the circulation. So in this way, I mean, this is the approach. This is the approach only I am saying, and many times question they have asked in GATE. Okay, it's very simple, very, very simple. So one by one I will explain here. Now we'll go through the basic idea about the this sign convention and all. So whenever sign convention if you are going to write for the circulation, sign convention for the circulation. So you have to write sign convention always, most of time in almost all book if you see, then anti-clockwise. This is the conventionally we are taking, you can say, or traditionally we are taking circulation is basically traditionally taken to be positive in the anti-clockwise. So anti-clockwise circulation, anti-clockwise direction circulation considered, this you need to remember, okay, considered as positive circulation, positive circulation. Like here I have given, suppose you are now, for this is the circle, and for this circle, suppose about this point you are writing circulation in anti-clockwise direction. In anti-clockwise direction you are showing the circulation, okay, or the big diagram also you can show. Suppose this is the circulation anti-clockwise, okay. So whatever the circulation you will have here, it is positive because it's anti-clockwise. That's the point only, okay, that's the point only. This is the sign convention first you got here. This is very important. Now you might have gone through the vector calculus. So theorem was there, Stokes theorem, Gauss divergence theorem. So if you remember Stokes theorem, okay, so if you remember Stokes theorem, so basically what is the Stokes theorem? So Stokes theorem basically use, I don't know how many of you remember Stokes theorem, Gauss divergence theorem, but it is in given vector calculus, engineering mathematics. So Stokes theorem is what basically used to convert line integral to surface integral. Means any line integral, if you want to convert into surface integral, then what theorem you will use? Stokes theorem. And how you will use, I will give the best example. Suppose, okay, example you just see, we have a line integral, we have, suppose this is the line A to B. So for this A to B line integral, and we have suppose this surface, okay, we can take surface area. So this is the surface area, and this elemental length for this we have dr, okay. Now if you want to check line, how to line integral will be converted into uh, uh, surface integral with the help of Stokes theorem. So as per Stokes theorem, if it is A to B, this is now line integral. See, along the length we are integrating, hence it is called line integral. So I am taking any vector quantity here, f vector, okay. So f vector dot dr vector, this is a line integral. As per Stokes theorem, if you want to convert line integral into a surface integral, so what you will have, because surface means area, so double integration will come. So to convert line integral to surface integral, or you can say from single integral to double integral, if you want to convert, then you can use Stokes theorem. So this is the surface. So you can write here S for the surface integral, and this value will be f, whatever the vector we have, f vector cross of, now it's cross of dr vector, okay, that's the mean of it. Cross of, not dr, it's just because now it's become a surface integral, so you have to write I'll cut, then write, this is the Stokes theorem, curl of f vector into n cap into ds. This is what is Stokes theorem. So in mathematics it is given, this derivation is also available for Stokes theorem, but here you don't have to go for the derivation, you have to use the formula directly. This is what is Stokes theorem. Okay, so here this is the line integral FDR. Now you want to convert surface integral. So instead of dr, surface area should come, ds, that vector should come here. Okay, n cap. Why? Because now you are having surface area, so whatever the perpendicular to the this plane, perpendicular to this area, that will be the n cap. Okay, if you go and calculate the value, so it is nothing but k cap, basically n, that is the unit vector, and perpendicular to the surface, obviously it will be the k vector, right? Because you are talking about ds, which is nothing but xy plane. So automatically it is, what about Stokes theorem? So Stokes theorem was basically used to convert line integral into surface integral, and once you will convert, then curl of f vector you will get, okay, into n cap, which is normal to the surface, and ds is the surface area or elemental area, right? This is the formula, direct formula of through the Stokes theorem I have written here. So now our formula, what is the formula we have? We have circulation, which is nothing but line integral of tangential velocity, okay, we have a line integral of tangential velocity, which is nothing but elemental length. We have taken ds. I told you ds is the elemental length. If you want to convert into surface by Stokes theorem, I can write here by Stokes theorem. So what I can write, I can convert into double integration. So it is nothing but double integration. We can put this symbol also, or we can write s also, meaning is same, and it is nothing but v theta. So we can write it's a curl v vector n, and ds, as I told you, this is the elemental length. So we can make it convert it into area. So now it becomes dA. Simple. Okay, so this was with the help of Stokes theorem. Now with the help of Stokes theorem, now you have converted this circulation, two formula you got. Now you can go with this second formula. This is the double integration. You can write s, or close value also you can write, curl of v vector. Okay, curl of v vector, it is n cap into dA, which is nothing but area. Now if you remember what is the curl v vector, it was curl v vector, if you remember last class I had explained, it was chi, which is nothing but verticity. I don't know you remember or not, and into dA. So this circulation formula, if you check what is the circulation formula, your circulation formula is now, let's come to verticity. From onward here you can see your verticity, which is nothing but circulation. If you check this eta into dA is the area, double integral, right? dA double integral and dA, you can say. So it is nothing but complete area. So now you can also say verticity also, it's a circulation per unit area. That also you need to remember. This is the very important point you got here. So your verticity or circulation, that relation you developed here. So basically circulation per unit area also called as a verticity. Okay, circulation per unit area also called verticity, that you need to remember. Now if you if you remember the formula of the verticity, what was the formula? Can you tell me for xy plane? Anybody, if you remember, can you tell me for xy plane what was the verticity? Xi value bolo, anybody? For xy plane means this will be xi z. What is the xi z? It is nothing but dou x minus dou y dou v dou u.
No, you.
Is nothing but, it's nothing but circulation by area. So this is very special result. Okay, this is very special result. This is very special result. You have to remember circulation per unit area. Okay. Anyway, now again, if you talk about the uh, rotational or irrotational flow, so here also you can check. For the rotational flow, circulation value will not be 0 because xi will not be 0, but for irrotational flow, uh, circulation will be 0. Okay, so it is now very clear. Irrotational flow, if irrotational flow comes, then you can say all points you can write. If irrotational flow is there, omega is 0. If I say omega 0 means omega x, omega y, z, angular velocity is 0. Then xi 0, xi x, xi y, xi z 0. Okay. Obviously, curl v vector also 0. Obviously, circulation is also 0. These are the points for the irrotational flow. So circulation also used to check the rotationality of the flow, means flow is rotational or irrotational. With the help of circulation you can check. We can check. That is the one thing you got here. Okay. Strength of circulation called vorticity. I should write here circulation per unit area. Circulation per unit area also called as strength of circulation. So strength of circulation also called vorticity, you need to remember. Okay, for 1 mark they can ask you. Okay, strength of circulation is angular velocity, strength of circulation is vorticity, strength of circulation is any other name they can give. So always remember, strength of circulation is nothing but vorticity, right? Correct. Now also you can define by this way, because now this is what vorticity, you are aware with this is what vorticity. So also you can make one more definition here. The circulation, see, you can also define the circulation is the integral of the velocity, integral of vorticity, sorry, integral of vorticity. Xi is nothing but vorticity. Integral of vorticity contained in the region enclosed by the circuit, means wherever the circulation is there, wherever the strength of circulation is there, if you take the integral of vorticity containing the region enclosed by the circuit, I will show you what is the mean of circuit. Then the integral of vorticity, see, this is the integral of vorticity or not, we have vorticity here, so this integral of vorticity also defined as a circulation. In line integral of tangential velocity also defined as circulation. Why I am repeating again and again, and why I am giving so much stress? Because those who have attended at this single time GATE exam, they are aware why I am repeating this. Because nowadays theory type of question they are asking, and they are manipulating theory, and more than one option will be correct. So that time the same for the circulation 2-3 definition they will give to you, and if you all definition you know, then you will mark the answer, otherwise you will be wrong. Nowadays multiple select question they are asking. They simply can give circulation is defined as, so if you are knowing this line integral of tangential velocity, you will mark immediately. But if you don't know, it is also the integral of vorticity. If you don't know, then obviously you will not able to correct. You will mark only one and you will be happy, okay, I have corrected. Yes, you are corrected. This is correct only, but this is also correct. So all definition, all formula you have to know nowadays. That is the GATE only. If you ask GATE is difficult, no, GATE is not difficult, but they are detailed information you should have if you want to crack GATE. Okay, always remember. Anyway, I'm not wasting here so much time. We are moving ahead, which is the next, which is called the center of vertex. What is the center of vertex? Or that part is what basically related to the circulation also. So what is the strength of circulation, that I have to mention first, then I will go for the next calculation. So strength of circulation, as I told you, strength of circulation also known as vorticity. Just now I have given the definition also. The strength circulation per unit area, also called strength of circulation, just now I have given. Now strength of circulation, which is nothing but vorticity, Now listen carefully. The circulation around a circuit. What is the mean of circuit and why circuit is coming again and again? I will explain you what is the circuit. Circuit enclosing the center of vertex, is called the strength of circulation. Okay, so now see, we have, this is the center of vertex. Now see, try to connect this. This is the center of vertex. Okay, this is the center of vertex, and we can have circulation around the center of vertex, that is gamma. Now for this particular gamma, if we are talking about the circuit, so circuit meaning is what? Suppose we can consider this is the center of vertex. I have to mention this. This is the center of vertex. Okay, and now we have circuit, which is nothing but, you can say, this is A, this is B, this is C, and this is D. So check, this circuit is what? Not including the center of vertex, because when circulation is defined, when strength of circulation will exist, when the circulation round a circuit including the center of vertex. But here center of vertex, this circuit is not including. Where is the circuit? This A, okay, A to B, B to C, C to D, and D to A. A to B, B to C, C to D, D to A. This is the one circuit. Okay, so it is very important. Always. If you want to calculate, or if you want total circulation round this circuit A, B, C, D, okay, then the center of vertex should exist inside the circuit if you want total circulation. If it is not existing, if total circulation you are going to calculate for this ABCD circuit, but your center of vertex is what? Not existing inside the circuit, then the total circulation will be zero. That's the mean of it. Okay, so if this center of vertex is not enclosing the circuit ABCD, then the total circulation will be 0. Okay, this point I have to write somewhere. It's very important. No? I have to write total circulation around the circuit. Just say ABCD. Round the circuit, total circulation round the circuit if center of vertex does not enclose, okay, center of vertex does not enclose inside the circuit, then the total circulation round the circuit ABCD, if center of vertex does not enclose inside the circuit, will be 0. Okay, so the total circulation round the circuit ABCD, if center of vertex does not enclose inside the circuit, will be 0. So to get the value of circulation, this center of vertex should inside the circuit only. This is the one property I have written. Next class I will prove. And based on this, 3 times GATE question they had asked for 2 marks. 2 marks. 3 times question they had asked. They had asked simply find out the total circulation. They had given the circuit also. And it was very lengthy question. But in one case, center of vertex was just out from the circuit. I mean, that circuit was not enclosing the center of vertex. If somebody know this property, then after seeing immediately they can mark correct answer. Option was there 0, pi, 2 pi, something was there. If somebody know this property of the strength of circulation, then immediately after seeing the question, immediately they can marks and they can get 2 marks. Okay, that mark, it was for 2 marks question. All right. Anyway, so we'll do that in next class. Up to here, I think that is for today lecture, it is sufficient. All right. Thank you.